So in today's lecture, I'm going to start discussion on data converters, and in data converters, analog to digital converter or digital to analog conversion process is going to be discussed. Now, we will start with the analog to digital conversion process, and in order to discuss the process, I can show you this basic block diagram. So the ADC process, someone is sneezing. Okay, so the analog to digital conversion process takes place in two stages. So the first stage could be termed as the sampling and hold operation, or the sampling and hold circuit, which will sample the input analog signal. And this, in the second stage, the sample signal is quantized and encoded in order to represent the analog signal into digital form, which is, representing it in terms of binary bits. So the conversion from analog signal to digital signal, first of all, the sampling has to be done, then quantization and encoding has to be done. So regarding sampling, you guys have a better idea than me at this moment because you are currently studying the signal and system course. So I think you have studied it in detail, what is sampling and what are the criteria that has to be satisfied while performing the sampling operation to a signal. So can someone just briefly state what is sampling and what are the criteria that must be followed while performing or sampling any particular signal? Anyone?
Sampling is like measuring the signal after a certain time period continuously.
Any other opinion? I mean, a precise opinion, anyone? Or a straightforward opinion?
Making continuous signal discontinuous can be called sampling.
Okay, so we have got two opinions. Now, both the opinions are uh, more or less correct, but in general, we can say that if we have a continuous signal, to convert the signal into an equivalent discrete form, that is the purpose of sampling. So after specific time intervals, if we take the magnitude of the signal and uh, the signal that the time interval whose reciprocal would be the sampling, termed as the sampling frequency, and it is following a certain criteria, then the proper sampling of a signal can be done. So regarding the sampling frequency, can you guys state the criteria that has to be followed in order to do the sampling operation in a way so that the signal can be reconstructed back to the original form?
The sampling frequency should be at least 2 times of the minimum signal frequency.
Yes, and that is actually the Nyquist criteria. So if the sampling frequency is twice the frequency of the input signal or the minimum component of the input signal, then the original signal can be reconstructed back again after doing the sampling operation. So basically, to convert an continuous analog signal into a discrete signal, suppose we can take the help of a pulse wave in order to do this sampling operation, and the frequency of the pulse wave would be the frequency of the sampling frequency. So just randomly I'm drawing a pulse wave. So in general we can consider that when the pulse is going to be high, we are going to actually take the portion of the input signal, and when the pulse is low, we're going to eliminate the portion of the input signal, or we are not going to consider the input signal for that moment when the pulse is low. So if we consider this sort of a pulse wave and we try to draw the sample signal, then for this portion of the pulse wave, suppose we are going to get this portion of the input signal, then when the pulse is low, we are not going to get any portion of the input signal. Then again, when the pulse is high, we are going to get a certain portion of the input signal again. Then it will be 0 again. Then again, we are going to sample the input signal. This way, this continuous operation is going to take place. And after a specific intervals, suppose after TS intervals, we are going to sample the input signal. So what the sample and hold circuit does, apart from sampling the input signal, it tries to hold the value before it is sampled again. So for example, here in this figure, I have drawn only the sampled portion of the signal. Now, if it is passed through a sample and hold circuit, then after a pulse is having a transition from high to low, this original the input signal, the sample signal is supposed to be getting back to 0, but if the holding operation can be if the holding operation can be incorporated along with the sampling, then the last value up to which we sample the input signal, that would be constant before the signal is sampled again. Then again, when there is a transition from low to high, the signal is getting sampled again. The output of the sample and hold circuit will follow the input signal. It will start following the input signal, and up to the point when the pulse is high, it will follow the input signal. Then it will hold this value before it is sampled again. So in this way, the sample and hold circuit will operate, and the purpose of holding or keeping the value constant for some time is to allow the encoding and quantizing and encoding operation to be carried out smoothly, because the analog signal, the input analog signal, is going to vary continuously. So before the quantization and encoding operation is completed, it might happen that the input signal has changed significantly. So in order to make the input signal stable for some time, or for a small duration, so that the quantizer or encoder can complete their task of quantizing and encoding, the sample and hold circuit is used, so that the input signal is sampled for some time, then it is held at its sampled value for some time, so that the quantizer and encoder can finish their task. Then after some time, it is sampled again, then kept constant, so that the quantizer can complete its task again. So in this way, after specific intervals, the analog signal is sampled, it is kept constant for some time, the quantizer and encoder then quantizes the sample value, and it encodes a binary some binary bits to represent that portion of the analog signal. Now what is sampling? That is again mentioned over here, that it is to convert an analog signal into a discrete signal. So the analog signal is continuous in time, and it is varying in magnitude. So both, I mean, it is varying with respect to time, and also its magnitude is varying along the change in time as well. Now in discrete signal, it is discrete in time, so that we are not getting continuous values. Rather, after discrete intervals, we are getting the values, but the signal may have different magnitude depending upon the selection of the sampling interval, which can be referred to as TS. So a typical figure is shown over here, where an input sinusoidal wave is sampled with an interval Ts as mentioned over here, and for this, after each Ts interval, we are getting a specific value of the sampled signal. Now again, the Nyquist criteria, which was stated a little bit earlier by one of your friends. So if the sample frequency is less than twice the input signal frequency, so FM here represents the input signal frequency, then a phenomenon called aliasing will happen that will restrict the reconstruction of the signal from the sampled data. So in order to discuss a little bit more on the aliasing effect, so the input signal frequency, which is FM, and the sample frequency Fs, which is greater than twice FM, in this case, which is following the Nyquist criteria, then if we consider the frequency spectrum of both the input signal and the sample signal, then we are going to have these two figures shown in our figure A and figure B. So in figure B, I mean, what we are getting after sampling, that we are getting a replication of the I mean input signal spectrum. So after each at each integer multiple of the sampling frequency, we are getting the replication of the input signal. So what is happening here when we are satisfying the Nyquist criteria is that between the repetitive frequency spectrums, there is no overlapping between two adjacent spectrums. So if someone wants to reconstruct the original signal back, so if a low pass filter is used, suppose whose cutoff frequency is set to be equal to FM, then the low pass filter can be used to extract the original signal from the sample signal, and any cutoff frequency within this range would be sufficient to, I mean, reconstruct the original signal. So for this case, it can be easily reconstructed. However, when the Nyquist criteria is not satisfied, then the repetitive spectrums will overlap with each other. So now if you try to set a low pass filter at the cut and set its cutoff frequency to FM, which is the frequency of the input signal, what will happen? It will, this window of the low pass filter is actually going to have or include the overlapping region as well. So the signal that you are going to reconstruct is going to be different from the original input signal. So in order to eliminate this effect, anti-aliasing filters can be used. So one criteria while using an anti-aliasing filter could be to set the cutoff frequency to be equal to half of the sampling frequency. So if this is Fs, this is twice Fs, then for example the half of fs could be lying over here, which is fs by 2. So if the cutoff frequency is set at this point, then majority of the overlapping portion can be eliminated. However, it will also eliminate some of the original input signal. So by using an anti-aliasing filter whose cutoff frequency is equals to half of the sampling frequency, the effect of aliasing can be minimized. However, exact reconstruction of the input signal will not be possible, but a fairly good reconstruction of the original input signal can be possible after performing or passing the signal through an anti-aliasing low-pass filter. Now, what is quantization? Now, a little bit earlier, it was mentioned that a sample signal is discrete in nature, but depending on the time interval, the signal can attain different magnitudes. But in order to represent the signal into equivalent binary form, there has to be some fixed intervals which would be, or fixed level of quantized states which would correspond to a specific binary sequence. For example, if a sine wave is sampled in this manner, so it is having some some different magnitudes after a certain interval. Now, if the sampling interval is reduced, then we'll again have even some more intermediate values. So different magnitudes can be obtained by choosing a certain amount of sampling interval or sampling frequency. So it is not possible to deal with each particular magnitude separately, because the purpose is to convert the signal into analogous digital form. So what quantization does, quantization breaks down this all the magnitudes of the sample signals into some finite number of quantized values or states. For example, if a signal is varying in a range from 0 to 10 volts, and if someone wants to represent this signal in terms of 8 distinct quantized levels, then for each quantized level, 10 divided by 8 equals 1.25 volts increment should be there. So any value of the input analog signal lying in the range from 0 to 1.25 would be referred to being the quantized level 0. Then after that, any value of the sample signal which is lying in between 1.25 to 2.5, that would be referred to quantized level 1. In this way, at each 1.25 increment, there is a separate quantized state, and each state has a particular range. Within that range, any value would be referred to that particular quantizer level. Now, how many quantized levels has to be chosen? That depends on how many binary bits is required or necessary to represent that particular sample signal. So if someone wants to represent each sample value by 3 binary bits, then the number of quantized levels has to be 2 to the power 3 or 8, like in this case. And if so for n bits, it could be said that 2 to the power n quantized levels will be necessary. So the more number of bits, the higher the resolution would be, or I should say the lower the resolution would be. I mean the increments would be reducing. So like it was mentioned earlier that if someone wants to represent in a sample signal by n number of binary bits, then 2 to the power n number of quantized levels is necessary, and depending on the the maximum and minimum value of the variation of the signal, like in previous example, the minimum value of the signal was supposed to be 0 and the maximum value was supposed to be 10. So the difference between the maximum value of a signal and the minimum value of the signal divided by the number of quantized states will give the increment between each stage. And this smallest analog change between each quantization state is actually called the resolution of that particular quantizer. So the smaller the resolution would be, the higher number of different magnitudes can be actually detected by the quantizer circuit. Now, after dividing the entire sample values into some discrete quantized levels, then it is necessary to finally encode a binary sequence with that particular quantizer level. So for the 0th quantizer level, the binary code should be 000. Then for 1 it should be 001. In this way, up to the last quantizer level, which is going to be 111 for 3 bits of representation. So to summarize the whole process, suppose a random analog signal is varying from 0 to 10 volts, and suppose if the signal is sampled at certain interval, suppose for some duration it is sampled, then the value is held constant for some time, then again it is sampled for some time, then again it is held for some constant for some time. In this way, a sample signal can be obtained. Okay, now if for each interval, if the sample value is considered separately, suppose this value is near to the 5 volts, or it is supposed between 4 volts 4 volts to 5 volts. Suppose this particular portion is lying between this range. So if this particular sampled portion is lying in between this range, then if we refer to this table, so this interval of 4 to 5 volts is referring to the quantizer level 3, which has a binary encoding of 011. So this portion of the signal will then be represented by 011. Then this portion, if this portion is considered, suppose this value is actually lying in between suppose 7 to 8 volts. And maybe the exact value of this level is suppose 7.5 maybe. So if it is 7.5, then we can refer to the chart. So from the chart we can either refer it to be at the quantizer level 5 or the quantizer level 6. So it could be slightly modified like this. If it is finishing at 7.50, so it should start with 7.51. Okay, so there could be some modification in this table, because both the intervals can't finish at the same value and start from the same value in the next state again. So let us consider that 7.50 is actually referring to quantizer level 5. So in that case, this portion would be defined by 101. Similarly, for this portion again, it could be suppose referred to as 011 again. Then this portion maybe it could be referred to as quantizer level 4 100. In this way, maybe last one is 10110. In this way, the analog signal can be first converted into its corresponding sampled signal, and from the sampled signal, depending upon the quantizer levels, a particular binary code can be encoded with the sample signal. So this binary sequence would be the corresponding digital representation of the analog input signal. So these are the steps involved in converting an analog signal into digital form. Now, if we discuss a little bit more on sample and hold circuits, so a typical circuit that can be used for performing the sampling and hold operation. So this basic diagram can be considered first. So suppose this V in and is an analog signal. There is a controllable switch over here, which can be any electronic switch like a BJT or MOSFET, which can be controlled using input pulse wave. And there is an output capacitor. So the voltage across the capacitor, let us consider that this would be our output voltage. So when this switch S is going to be closed, then the input signal is going to be passed towards the capacitor, and the capacitor will charge according to the magnitude of the input signal. So this capacitor voltage Vc will follow the input signal for the period when the switch is closed. Then when the switch is open, then the capacitor is not supposed to have a path to discharge itself. So it is supposed to hold its value until switch S is getting closed again. So in this process, by in continuous period, by closing or opening the switch S, the input signal can be sampled, uh, uh, and the sample value can be held constant for some time, as the voltage is going to be stored across the capacitor. So a more practical circuit which can be used is this one, where two op-amps are used as buffer circuits. So whatever the input voltage is provided at the non-inverting terminal of the buffer, that is going to be obtained at the output side as well. Now this input is going to be transferred towards the capacitor when the switch Q is closed. And for this particular example, this switch Q is considered to be a P-channel MOSFET, or a PMOS you can say. Then from the capacitor, suppose this is capacitor voltage Vc, that is passed through another buffer circuit. So this buffer or voltage follower will again transfer this voltage across the capacitor as the output of the buffer. So this VC is going to be the output of this particular circuit. So, okay, yes, he has turned off his mic. Okay, as this, for this example, a P MOSFET is considered. So the considering the pulse wave, the PMOS will be on when the pulse is low and the PMOS will be off when the pulse is high. If it was an NMOS, then the inverse operation would have taken place where when the pulse was high, the switch was supposed to be on. When the pulse was low, the switch was supposed to be off. But as for PMOS, the inverse operation will take place. So when the pulse is low, the PMOS is on, which means that for this period of time, the data is going to be sampled, and when the pulse is high, the switch is off. For this period of time, the capacitor is supposed to hold the value constant for some time. Then again, when the pulse is low, the switch will be closed again, and the data is supposed to be sampled again. Now, in this particular figure, this solid black line is representing the input signal. Or input signal is represented by this solid black line, and the dotted line is actually representing the output of the sample and hold circuit. So as long as the switch is on, the capacitor is supposed to follow the input signal up to this portion, ideally. But when the pulse is having a transition from low to high, the switch will not get closed get open or turn off instantaneously, but it will require a small amount of time to completely turn off. So even after the transition from the pulse, the capacitor will still follow the input signal for some time. Then it will try to hold the value constant before there is another transition in the input pulse wave. So ideally, the capacitor is supposed to hold the value constant at the level up to which it was charged. But in practical case, there will be some decay as shown by this dotted line because of some leakage current flowing through the capacitor. So this leakage of the capacitor depends on the amount of leakage current. So for the capacitor, if we consider the leakage current to be I, the I can be related to the capacitor C, capacitance C, and the voltage across the capacitor VC through this simple equation. So this droop rate of the capacitor then can be represented as VC by VT equals C divided by ID. So ID can represent the droop current, and this one can represent the droop rate for which the capacitor is getting decayed. Capacitor voltage is getting uh, uh, discharged by a little amount. So the the time which was required for the switch to turn off completely or the switch to become open completely, that time is called the aperture time, and the rate of decay of the capacitor is called the droop rate. And after there is another transition from in the pulse wave from high to low, then the switch is again supposed to be getting closed or turned on, and the capacitor is supposed to follow the input signal again. But as the capacitor was already containing some amount of voltage, or it had already stored some amount of voltage previously, so it will not be able to instantaneously follow the input voltage or track the input voltage. So it will also again take some time to rise up to the level of the input voltage. Then it will actually start following the input signal again, or track the input signal again. So this duration which is required for the capacitor to track the input voltage again, that is called the acquisition time. So this aperture time, droop rate, and acquisition time, these are some of the response parameters of a typical sample length hold circuit. So the aperture time, the droop rate, then the acquisition time, this should be controlled depending upon the requirement of the particular, or the accuracy requirement of the particular ADC. So one question I can ask to you, that along with this capacitor, we have connected a voltage follower over here, or a buffer circuit. So what possible advantage can we get by connecting this buffer circuit with without taking the output directly from the capacitor? So what could be the possible advantages of connecting this buffer circuit?
It will nullify the loading effect.
To nullify the loading effect, and what would have been the problem if there was a loading effect?
So due to loading effect, the overall impedance of this holding circuit will be affected. Then the signal will not be able to hold as much as it would hold if there were buffer circuit.
Okay, and another thing you can mention over here, or add to your explanation over here, is that if there was a loading effect, then the capacitor would try to get discharged through that load, or the load resistor, when the switch Q is supposed to be turned off. So in order to minimize that effect, the buffer circuit can be useful, because you know that the buffer circuit is normally has a high input impedance and low output impedance. So if there was no buffer circuit over here, you were taking output from across a load resistor, then the capacitor would try to discharge uh, through that particular resistor when the switch Q is closed. But when you have the buffer circuit, these two terminals of the op-amp, the non-inverting terminal and inverting terminal, is suppose going to provide a high input impedance, which is ideally could be referred to as infinite, but it cannot be infinite. So due to this present of high input impedance provided by the buffer circuit, the capacitor voltage would not be able to get discharged easily. Some amount will be discharged due to leakage, uh, due to small leakage current, but it would minimize the discharging of the capacitor voltage. And overall, both the buffer circuits are actually used for minimizing the loading effect, and in order to perform impedance matching, so that the signals that doesn't get distorted too much. And the proper choice of the value of capacitance is important as well, because depending upon the value of the capacitor, both the droop rate and the acquisition time will be affected. Because for the acquisition time, the capacitor will actually have a charging time constant of suppose RC, where R can be referred to as the on state resistance of the switch Q. So the value of C should be chosen in such a way that the charge constant is not too high, so that the capacitor will require too much time to get charged to the level of the input voltage. Then the acquisition time will increase. So it should, from this regard, the value of C should be as minimum as possible. But again, it will have a low value. If a low value of capacitor is chosen, then it would I mean affect the droop rate, because the droop rate is supposed to be then increasing. Okay, we can refer to this expression here. So here, okay, I have made a mistake. It should be ID by C. So if the C is decreasing, the droop rate will actually increase. And if C is increasing, the droop rate is going to be decreasing. So these are two opposing phenomena. So in order to minimize the droop rate, a high value of capacitor is necessary. And in order to minimize the acquisition time, a low value of C is necessary. So a trade-off between the two is necessary. A capacitor value should be chosen in such a way so that the acquisition time is not too high, and also the droop rate is not too high. So uh, some intermediate value of capacitance has to be chosen, so that the both the effects can be within some tolerable limit. So the definitions of the response parameters and the consideration for choosing the value of C, these things are summarized over here. You can later on go through this, and for this portion of discussion on sample and hold circuit, you can refer to chapter 2 of NMS Anand. From there you might have a little bit more detailed idea about it. So for this particular class, I wanted to discuss up to this point. Now, up to this would be your midterm syllabus. So our discussion on data converters was supposed to include the different types of ADCs, then DACs. So there are different types of analog to digital converters, like flash AD converter, successive approximation AD converter, then dual slope AD converter, delta sigma AD converter. So the operating principles of this type of AD converters, we will start discussions on this after your midterm exam. So up to for your midterm, up to the sample and hold circuit would be your syllabus. Now, if there is any question, anyone?
Sir, will you give some math examples like you did for the previous quiz?
For the midterm?
Yes, sir.
Yes, I suppose from the topics which were discussed beyond the syllabus of your quiz 1, I'll try to highlight the reference articles and some of the math example problems that you need to solve. I will try to make a summary, and by today or by tomorrow I will give you those I mean article numbers and example problem numbers.
Okay, sir.
Okay, any more questions or queries? Let me discuss something then regarding your midterm exam. So your exam is scheduled on 21st November from 10:30 to 12. So 1.5 hours is allocated in total for your exam, but your exam the exam will have a total duration of 60 minutes. So the exam duration will be 60 minutes and the marks of the exam will be also 60 marks, and you have to answer 3 questions out of 4. So 4 questions will be given. You have to answer 3 questions. Each question will have 20 marks, and roughly you should finish answering each question within 20 minutes. And for each question there could be multiple subsections, suppose 2 or 3 subsections, but the question would be such that if it would be each question you would be able to answer within 20 minutes. So the questions might contain some of the derivations that were discussed during the lectures, or there were some theoretical discussion regarding some working principle or operating principle or characteristics of different uh, type of transducers or different types of errors, or regarding the whole discussions. Some theoretical questions might be there, some derivation might be there, and some math problems would be there. So for the math problems, you need to go through the example problems thoroughly, so that if there is slight changes in the question, you can answer it, because you might not get exactly the same question that is given there in the examples. The concepts of multiple examples can be merged together, or uh, the values could be changed. So uh, while you go through the example problems, you should try to understand the different steps involved in the math.
Sir,
Yes,
the exam time you are writing it's from 10:30 to 12. That's 1 hour and 30 minutes. But your exam duration is will be 60 minutes.
yes, I said that in the routine it is allocated from 10:30 to 12. So suppose I'm going to take 60 minutes for your exam, then I will give you 10 to 15 minutes to make the PDFs of your scripts and upload them within the next 10 to 15 minutes. So within 12 p.m., I think before 12, we would be finishing all the proceedings. I mean the exam and the uploading the PDFs, everything. But do you guys want to have a 1.5 hour exam, or I mean, what is your idea about it? If you guys want to appear a 75 marks exam of 1.5 hours, then I can do the question like that. So it would be like a regular midterm exam. Anyone? So a 1 hour exam or 1.5 hour exam? What do you want?
1 hour exam is all right, I guess.
So 1 hour exam feels reasonable enough. So.
So on the same day, your CR contact. Yes, anyone is saying something?
Yeah, I wanted to say something.
Yeah.
Regarding the mid exams.
Yes.
Hence, we are still going online, and we have seen that most of our teachers, our other engineering courses, although they are going to set the questions like the same, but they suggested that they will give us like 3 questions, and we will answer any 2. There will be option of 3 questions, and we will decide to answer any 2 questions. So I think with regards to the time to answer 3 questions in this online exams, it's going to be a little bit difficult.
It would not be difficult because although there will be 4 questions, but it doesn't mean that the question length would be similar to what you guys get in physical midterm exams. So it is actually a relative thing. Okay, it doesn't mean that if someone is giving you 3 questions, he is asking you to solve 2 questions. The 2 questions might be so lengthy that you cannot finish within 1 hour. So that could be the case as well. So it is a relative issue. It is not something like that. Uh, 4 questions out of 3 out of 4 would be impossible to answer within 1 hour, but it depends on how much you have to write for each question.
That's right, sir.
Sir?
Yes.
When it comes to the maths questions, all the chapters, like I'd say, majority of the chapters, they all have maths problems. So, are you going to set in any of the chapters where you are going to specifically tell us to revise a certain chapter where you are going to set the maths questions? Because we have too much of maths questions there.
Now, in your book, there are several math problems or example problems, but I would give you some example problem numbers which are related to the discussion that I have conducted. Okay, so you have to go through only those example problems which I specify, but from your book, the other example problems which are not directly related to the discussion that I conducted, you can omit those example problems. So I said that I will highlight or summarize the article numbers and also the example problem numbers that you need to do. So go through only those example problems that I am providing you, and from those example problems similar to those you will find in your midterm exam. And I am repeatedly saying this, that don't expect that you are going to get exactly the same question from your book to be given in your exam question. There might be some modifications. So while taking preparation, don't just go through the examples and try to memorize those. So that is not going to help you. And also in the previous class, even one of the students I pointed this issue, and also I told the same thing, that in the solutions of those example problems, there are some minor mistakes. like the formula is written correctly, but the final answer is not correct because they are not putting all the values of the different variables in the formula. So for these sort of issues, while solving the example problems, you should keep those things in mind. Don't try to memorize the example problems and think that the exact problems are going to be coming to the exam, and you can just recall from your memory and write it down.
Okay, thank you, sir.
So will there be derivations, like formula derivations, etc.?
Yeah, I told you that there would be some derivations. There could be some theoretical questions like definitions or some characteristics or advantages or disadvantages of different topics which are discussed. So derivations should be there. So
Yes, sir. Thank you, sir.
you should take preparation accordingly. Now, I had a discussion with your seer, and he informed me that it is convenient, or everyone is agreeing to give a quiz on the same day as the midterm exam, which is 21st November. So I could take the quiz from 2:30 p.m. and the question pattern for the quiz would be similar to the pattern which was followed for quiz 1, and the syllabus would be the AC bridge circuits and the transducers up to slide 49. So that is the topics which were discussed before optoelectronic detectors. So this would be your syllabus for the quiz, and similar to your first quiz, there would be multiple choice question and short questions, both in the form of some theoretical short question and some mathematical short questions. Any other queries today, or maybe some questions or query might pop up in your mind later on, so you guys can share your queries with the seer, then the seer can contact me if necessary. Other than that, you must start taking your preparation, and I'll try to summarize the topics, the article numbers, and the example problems, and post it as soon as possible. And before the exam, I'll try to give you some guidelines regarding how you have to attend the exam, how you have to upload your answer scripts. So I would try to give some guidelines later on. So you have got a general guideline from the department where you have some ideas about the exam process, where there would be virtual invigilation. So several teachers are going to be there. You guys are going to be divided into several groups. So which group is going to be under which invigilator, and how you're going to get the question, and how you're going to submit your answer scripts. Regarding that I will have a separate discussion later on. So if there are no queries, I am terminating today's session.